Okay, great. The first stream had to be stopped, so right now it's deleted, and we have to use this one because what was happening was that the microphone wasn't working. So right now it's working. Beautiful. So let's begin so that we don't waste any more time. Yeah. Okay. So we've already done everything up to this point. We've been able to talk about congestion control, everything during the last time. Right now, what we want to do is to just quickly run through the network layer and the data link layer or the link layer, and then the next time that you see us, it might be for some solving of questions, right? Yeah. So that's how we do it. And also, I realized that to explain the CIDR, the classful classless subnetting part would require you to like it requires questions, right? So I've decided to put it off for a little while, right? So we'll solve questions with it. So I think that's the only thing we'll not be doing, but hopefully we'll clear the entirety of the network layer tonight. Okay, let's go. Beautiful. So first of all, we'll be talking about the data plane. Please hold on for me. Okay. 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 So we'll be starting with the data plane. So, so the data plane talks about the local per router function. This word will come back to hunt us again. So it talks about the local per router function. That is normally we talk about router functions. It's normally forwarding that is the router function. There's nothing really that comes just forwarding. And then when you talk about the global function, right? It's the it is routing. I think that's the only thing you need to know right now, like about the generalized or is being generalized. Oh, um, to the slides. Okay. So, oof, no, this is necessary, right? So we just talked about it that you have two functions, forwarding and then routing. Forwarding talks about moving packets from a router's input link to an output link. What that means is that you can have some router that has several inputs and several outputs. So A, B, C, D, E, F. And then you don't know what is happening, but all the links may be in use at once. So what will happen is that because their routers are normally in full duplex, communication can happen both ways at once. That's right. So what's happening is that it may be a packet from A to E. So the process of it moving from A to E is called forwarding, and it doesn't just happen like that. If you remember, we said that there must be some header removals, there must be some decapsulation, there must be some encapsulation again. To understand because this router is a router, it can like it's a layer 3 device, so it can touch the network layer, the link layer, and then the physical layer. Understand? That's where it's coming from. And routing is to determine the path from source to destination. The analogy that really helped me understand this was the trip taking analogy, right? So you're moving from Kumasi somewhere else, and then the process of getting through that single interchange, or getting to that single junction, or getting through a gate or something is the forwarding, and routing is knowing which paths to take, right? You are still you're taking a path from here to Tamale. You don't start off by I don't even know. I don't know what I was about to say. But a simple example would be that you're taking you want to move to Brunei and then wow, you start by going off campus. It doesn't really make sense. So routing is the process by which you find out the paths, the full path from beginning to end. But so yeah, so we talked about data plane being local, the control plane being network wide logic. Okay, so let's start with it. So what's a router? What's a router? A router is a principal network layer device. Router. This is the device, right? It's the principal network layer device that sits in the network core. That's basically what a router is. And what a router does is that first of all, the most important thing a router does is to move datagrams from input port or link to output. And then the second thing a router do is to examine the headers. It just examines headers datagram. It will look at the headers, and then based on this, when we go forward, we'll talk about destination based forwarding, and then we'll see why a router actually why it does this. You understand? Okay, cool. I think we can skip a lot of things. Okay, so what are the approaches to implementing a control plane? Right. The first approach is the traditional routing algorithms using routing algorithms. The second approach is an SDN, right? So this particular one uses a distributed or decentralized routing algorithm, right? Routing algorithms, and an SDN normally uses a link state algorithm. Yes, both of them use algorithms, but this is usually distributed. We'll get to know what that means as time goes along. Right. So with the traditional approach, right, the traditional routing algorithms approach, what happens is that each router, right, each router runs its own like what it thinks should be the cost, like what things should be the cost in traversing all the paths. You understand? It runs its own algorithm. Each router runs its own algorithm and then communicates it to the others, right? And in the SDN, software-defined networking approach, what happens is that there's a particular server sitting somewhere that knows it knows the information about this, and then it implements, it tries to find the link. Right, it tries to find the link. This is node A. It tries to find the connection between all the paths, you understand, and then builds a forwarding table out of this. Right? And because it's a server, reliability comes in, computational cost comes in, right? A router is a like usually it's a small device. It's not really like a large device like it can fit into a room. No, it's a smaller device. But these computers sitting in data centers are larger, does have more computing power, so it can look at the entire system and then calculate all the link costs. You understand? And so that's the traditional approach, and then the SDN approach. Right. So what is the service model? Right now we're getting into the weeds. Right. What is the service model for the network layer? So what a service model is basically the kinds of services that a network layer guarantees, right? So what does a network layer do in terms of services? That's what it's basically like. That's what we are basically asking, right? The properties of the service. Now, the name of the service model for the network layer is called best effort service. Understand? That means that it will try its best, right? And its best meaning that it will just send it out into the world and like those things they were explained to be fake. They were explained to be false some time ago. The baby birds thing. Ah yes, that's what they're going to do. They're just going to throw the baby birds outside the nest, and then Is it? Okay, so what happens is that you are just going to try your best. You just send the IP datagrams into the world and then hope for the best. You understand? So these are the guarantees, right? The guarantees are that it is guaranteed not to be delivered to your destination. Right? The IP datagram does not guarantee that you get delivery. You understand? It doesn't guarantee that. Right? Datagrams are not guaranteed. It's not guaranteed that you get like a specific time. You understand? Like there's no specific time frame that the network layer just like it doesn't guarantee any time layer or bounded time. You understand? Right now you can have some application layer services, some web services that guarantee that if you don't get a response in 30 milliseconds, right, send another request because it's been lost. Like they're giving you a bounded guarantee that in 30 milliseconds you should have gotten your answer or something else has happened. Understand? That's a bounded guarantee. So guaranteed not to be delivered with a specific delay. Understand? It's not guaranteed. But the third thing that the service model describes is that it's not guaranteed to be delivered with some minimum bandwidth. These are all guarantees. Like it doesn't guarantee any of them, right? It doesn't guarantee that you can send a movie, a 2 gig movie, and then it will because the bandwidth is constant, right? It will get at the same time. No, it doesn't guarantee any of that, right? But there's some new services right now, still application layer services that look at your system and then can give you a guarantee of when your thing will finish downloading or when your thing will finish uploading. You understand? That's a minimum bandwidth guarantee. You understand? Beautiful. So the network layer has um um has zero guarantees on um, delivery, has zero guarantees on delay, has zero guarantees on loss, has zero guarantees on the order that your packet will arrive in. You understand? So yes, so we can move on. So these are service models. So if you see any question like which of the following are service models, is the service model for network layer, or which of the following describes the best effort service? I've seen a question like that. Which of the following describes the best effort service of the network layer? It doesn't guarantee anything at all. It's just let's see what happens. That's how it feels. Like, let's just see what happens. It doesn't guarantee time, order, um, loss, delivery. It doesn't guarantee anything. Okay. But because it doesn't guarantee anything, you can build things on it. I feel like that's what we miss. The fact that it doesn't guarantee anything, that means that you can implement whatever you want to. You understand? They just made it easier. It's like you don't have to go and look for your own sand. You don't have to build your own foundry. You don't have to do anything. But somebody has built a microprocessor for you, and then you can write code on it. It's a beautiful experience. You understand? Like the in the past, you had to do your own thing yourself. But right now that you can have foundries that can do any type of fabrication for you. It's very simple. And it doesn't guarantee anything in you, like your code will work or anything, but that gives you ability to build any type of thing you want on it. That's why the service model for the network layer is it's great, right? It's actually great. You understand? Beautiful. Now we can move on to that was weird. Okay, so we can move on to destination based forwarding. Okay, so what's a destination? Aish. What's destination based forwarding? Destination based forwarding is basically looking at the IP address of the IP address which is in the header of your datagram and then routing it according to a setting, like passing it to a link. You understand? The reason why this is important is that yeah, so this question came up, right? This question came up. What is please hold on for me. Okay, I'm back. Right. This question came up. What was I even trying to? Yes, this question came up. What is the length of a UDP header? It's not a past question. It was a fresh question that came from our time. Maybe I didn't see it yet. The answer is 8 bytes. So if If it comes again, please don't. Yes. So an IP address is 32 bytes. Hey, let's say bytes. 32 bits. Right. This is bytes. This is bits. Right. That means that it has almost 4.96 billion like addresses that you can address. You understand? 4.96 billion. And the issue with this is that every single interface in your system has an IP address of some sort. You understand? That means that your phone, the laptop you're using, the Apple watches, the normal watches, the phones, tablets, right now everything, smart fridges, BBR, everything has an IP address. You understand? Because of this, they realized somewhere in 2011 that it was going to finish. You understand? We'll look at two mitigation strategies that they came up with, like to stop to stop it being finished. Because if it finishes, and everybody on the internet is supposed to have a unique IP address. And if um people in the US have IP addresses and then people somewhere else don't, what happens is that you'll not be able to join any network. Right? If you join any network, okay, that's a mitigation strategy. But how it was that you couldn't join any network. You join any network, you can't send messages because IP address, like what the IP address allows you to do is to provide an address for you to know when messages are coming from, messages are going. Understand? We'll talk about all those things a little later. Great. So I talked about IP addresses being 4.96 billion like different devices that you can get to. That means that if I give you any address, right, the probability of finding it is very rare if you just do it randomly, 1 over 4.96 billion. You can't, don't try it. Understand? So what happens is that we came up with this, right? It's a table. It's a table. And this is what destination based forwarding is. The problem is that there are too many addresses to go through. Right. That's the problem of destination forwarding. How do you send the message how do you send the message to where it's supposed to be sent to? You understand? So this is destination. And this is the output link or link interface 1, 2, 3. And then this is address 1, 2, address 2, address 3 to address 4. And this is normally otherwise. The last one is a default. The last one is a default. So what happens is that basically, when you get any address, right, you just check which range is in, and then you send it out the output link. That's destination-based forwarding. And these addresses are IP addresses. These addresses are basically IP. You can't match it with anything else in destination-based forwarding. In destination-based forwarding, only IP addresses are used for matching. You can see you get a question that says that, oh, in generalized forwarding, which of the following cannot be used? Something like that. We'll talk about generalized forwarding. But in destination-based forwarding, only IP addresses, right? Hey, let me clarify that. Let me clarify. Only destination IP addresses are used. Source IP addresses are not used, right? Only destination IP addresses are used. And then that is what is used to forward the messages. You understand? Right. So there's a way of efficiently, everybody's looking for efficiency nowadays, right? There's a way of efficiently identifying which range like an address belongs to, right? And it's called longest prefix matching. Right. With this, the interesting property about this is that there's something called complexity. We'll meet it when we talk about routing algorithms, right? Big O notation. And this has a complexity of O1, meaning that no matter how your addresses or no matter how your table is for anything, it only takes one cycle. You can think of this as like a cycle from micro P. It only takes one cycle to get your address to find out which it belongs to, right? Previously, you would have to actually go through like manually to see where it goes in, or it was never done, but like that's how it's implemented. The longest prefix matching, like no matter how long your address is or no matter how large your forwarding table is. This is a forwarding table, by the way. No matter how large your forwarding table is, it will always take one cycle. Like you see, there's beauty in that. You understand? There's beauty in that. How the longest prefix matching works is, so this is the first one, right? How longest prefix matching works is that there's a destination address range, but it's not the same. It's not the same. It's more of like this: 11001000. Then you have maybe star 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 star. What happens is that these stars are donkeys, right? Every star is a donkey. So okay, another one star star star. It's a 000 star star star. So if you see something like this, right, and you get an address like 11001000, let's say 11, ignore the rest, it's not important. Something like this, you get something like this. What will happen is that is saying that if the address starts with this, we don't care what the rest of the values are, send it to output one. And if it starts with this, we don't care what the rest are, send it to output two. So what will happen is that um the leftmost bits, the leftmost bits, right? The MSB of the address must match the like the this MSB must match this one. It's the most significant bit. And the rule is that the longest prefix is the one that becomes the appropriate destination. So what that means is that let's say we have two addresses like link one and link two. And link two's IP range is 1100100011. And this one is 11001000 star star. They're basically the same, but this has a longer prefix. And then let's assume, yeah. So this one will go to output link one. Not because this doesn't match, not because output link two doesn't match, but because one gives you the longest matching prefix. The longest prefix that matches. You understand? Yes. So that's what happens. So you can get a question like for this particular address, right? Which of the output links would it go to? It can be like one of those, use this table to answer 11, 12, and 13, those things on, and then it can come like that. You understand? So what you do is that you look for the longest prefix match, and then you pass it to that's the one. And so yeah, so be very careful about what you're picking. Okay. Okay, so we've finished it. Let's move on to IPv4 and addressing. Yes, as I said, I don't know whether you didn't hear, but I won't be touching the classes, right? We'll be doing some more. And then as you're solving the questions, then we'll talk about the classes A, B, C, D, E, talk about the classless addressing, talk about the default subnet masks and all those things. We'll solve questions with this so that it gives you more understanding. And basically we're just running through it, right? So what's a forwarding table? We talked about a forwarding table, and a forwarding table is basically like it's a local, okay, it's a local database, right, of addresses and links that determine which output link a router is supposed to forward a particular packet to. Understand? So yes, an IP protocol. So this particular IP protocol, the one we just talked about, that has no guarantees on anything, It's a protocol or set of rules. And the reason we see this is important too, right? It's a protocol and set of rules, and it's concerned, right? It's concerned with a couple of things. It's concerned first of all with a datagrams format. So it talks about what is the format of a datagram. We'll look at it. We'll draw a datagram and we'll look at it to look at the parts and what they do. Also concerned with how IP addresses are structured and interpreted. And thirdly, it's also concerned about how packets are handled. So these are the three things that the IP protocol talks about. It doesn't talk about anything like anything outside the scope of this is truly outside the scope of this. You understand? So allow it to wait. This I promise that we'll look at the IPv4. Oh, we've not talked about virtual circuits. Okay, so let's talk about virtual circuits. Let's talk about virtual circuits. Something that I keep missing. So there are two types of networks, right? There are two types of networks. If you remember TCP, and we talked about the fact that one is connection oriented and one is connectionless. Please excuse me. Okay. So we talked about one being connectionless and one being connection oriented, and I hope you remember. But as UDP is connectionless and then TCP is connection oriented, that means that there must be some sort of initialization before your system can sort of like a boot up, right? There's supposed to be some sort of greeting before begin. A way of thinking about it is that if you're talking to someone you don't know, you understand, you're talking to somebody you don't know, you always start with, oh, hello, good morning, that sort of thing. But if you're going, for example, you're going into the room of somebody that you really know, like, you don't have to knock. You understand? You just enter and then, like, you just go and take the book, or you ask for the book or anything that you want. You understand? There's no sort of initialization involved. And that's how it is, right? UDP refuses initialization, refuses connections, and then TCP expects or requests a connection before it begins. So at the network layer 2, there are two types. You can have a connection oriented service. And this one is in the slide. You can have a connection oriented service or a connectionless service, right? And the connection, like the service that requires a connection, is called a virtual circuit network, a VC network, right? And the one that doesn't require it is called a datagram network. You understand? Connectionless service, yes. Okay, so you just let's move on. Okay. Yes, beautiful. So one uses in the VC network against the datagram. The datagram is just this is truly the best effort service. It just moves along like nobody's business. But with this one, there are three phases, right? In setting up your network, there's a setup. That is when your system talks to each other to generate a path that it passes through. You understand? And then there's a maintenance. The maintenance like deals with making sure that your connection is up. You understand? If you realize that, oh, there's been a break or something, it will have to set up again, right? There's encryption and all of those things, but let's not get into that. And then there's a tear down. This is when you are done with what you want to do. You finish sending all your information. You really just want to tear down the service, because what happens in the VC network is that there's a literal virtual circuit. Like you're trying to implement a virtual like a circuit that like you're trying to virtualize circuit switching. Circuit switching, there's a path that it flows through, and you don't just change that path. You understand? There's a path that it flows through that it must always flow through. So that's what it is meant to do. So you have to tear down. I saw a question like this, right? Talking about which of the following is are not like phases of virtual circuits, like just working with virtual circuits, and these are the three phases involved in it. Understand? I don't think there's anything that's like you really need to know inside. You don't need to know anything that's inside. Yeah. So let's we're going to talk about IPv4. Okay, so yes, I've gotten where I wanted to get. So I wanted us to get to I wanted us to get the diagram, the format of the IPv4. Okay, so we've gotten it. Right. Now, this is important. This is very important. I don't know whether I might lose fact today. So this is it, right? You have the TCP header being 20. You have the IP header being 20 bytes. That is. So in the IPv4, this is IPv4. You have a version number. Right? You understand? This is a type of service header. If you remember that we used to talk about congestion control. You understand? So with that particular one, you change it's zero, and then the router changes it to one to indicate congestion in the system. You understand? Yeah. I think remember that explicit congestion notification. Right. Then the diff serve is used to differentiate between different classes of traffic, right? Which can be given different services based on the traffic class. Like yeah, that makes sense. That makes sense. I was come to that makes sense. This is the length, right? This is the length of the total datagram. You understand? This is the time to live field. So what happens is that there are some, because when you send a message out, right, when it gets to the router will use like the router generates a new, not like it's your same message, but it sends out a stronger signal, like it sends out the same. Yeah, great, great. Okay, let's get to it. Right. What's an IP address? We've talked about this. What's an IP address? See, an IP address identifies an interface, right, on a host or a router. What it basically does, that identifies interface, right, that is like connected to the internet. How do I get an IP address? And this is the protocol that's in charge of that, right? This particular protocol is in charge of getting people IP addresses. Like, see, there are 4.96 billion addresses, right? So it is responsible for giving you one of this 4.96 billion. Okay, good. First of all, what happens? Right? What happens? Um, he laid it out pretty good here. So let me use this one. But as we are going along, DHCP is like it's divided into four, right? We have four messages or four things that make up DHCP: the discover message, the offer message, request, and act. Both of these are optional, meaning that you can actually start from request and act, and we'll see why. We'll see why very soon. See why very soon. Okay, cool. Okay, cool. So you have this, right? You have a particular DHCP server sitting somewhere, and then there's a client that's arriving. Normally, this Wi-Fi. You understand? So the phone comes on and then connects to the Wi-Fi. Those few seconds, and what's happening is that these four steps are going on. So I don't know whether you've actually seen it. I've seen it on my phone before. You try to connect to the Wi-Fi, and then they will let you know IP config failure. That's most probably that this is what's happening. There's a problem with the DHCP server configuration. Maybe it has gone down. Maybe the router cannot connect to the DHCP server. Maybe it's not understanding your message. Plenty things can happen. Right? One thing I've not mentioned that, but that's actually very important, is that if you um if you set a destination, right? Let's say that you make your you have an IP address and it says this 255.255.255. This is called a broadcast address. This is called a broadcast address. What this broadcast address means is that whatever subnet is connected to, it will send it to every interface. So when this is your address, this doesn't point to like a specific phone or something that's sitting somewhere. This points to a particular, like it points to like broadcasting. So this one, when any router sees this, it will send it to all the sorry. When a router sees this, it will send it to all the interfaces that are connected to the particular router. You understand? Okay. So this is the broadcast address 255.255.2. Let's move on. So what happens is that what happens when it starts? So what happens is that when you connect to a particular network, right, your source IP is 0.0.0.0, and then you send um a broadcast message. That means you're sending to 255.255.255.255. This is because you don't know what's the DHCP server, like where it is, right? But normally, right, normally there's a DHCP server sitting in every single router or connected to every single router. Meaning that like whatever router you have, if you send a message, a broadcast message to it will hit a DHCP server somewhere, right? And I think I saw some research on implementing DHCP in routers so the routers can keep track of what is going on. Understand middle boxes and such. So it doesn't have an IP address, so it uses 0.0.0.0, and all hosts on the in the subnet, right, or connected to that particular router receive the discover broadcast message. It receives this message. Everything receives this message, and then the transaction. So you see something like transaction ID. That's how it keeps track of it. Right? I feel like these messages are some way, but that's what happens. So when the DHCP server sees the message, if you are a host and you see a discover message, you ignore it. You don't work with it unless you're working with a P2P scenario, and then that's something different. But if you're a normal host and then you receive a message, I just ignore it. So only the DHCP servers would reply. So when you get an offer, right? When you get an offer, what happens is that the DHCP server will tell you that, oh, here's an IP address that you can use, and it sends it to 255.255.255.255. So if you are an arriving client, you get the message too. You understand because you are temporarily connected to the network. And if you have an IP address and you get this message, you can ignore it. You ignore it. Great. So it is sent to all the interfaces. And so what happens if, for example, because there's a lifetime that you can use an IP address for. It's not forever. Every 1 hour you have to, depending on how your DHCP server is configured, every amount of minutes you have to like do this process again. So what if you're using like you had an IP address already and then you were exhausted, like your time finished and you are requesting for like same IP address? Or what if someone told you that, oh, you can use this IP address, or you've connected to this network before and want to use the same IP address? All of these you use the DHCP request. That's why these two are optional, right? They're optional because you can move straight to the request if you have an IP address that you can use. You understand? So this is it. It's great. So with this, you tell the DHCP server that, oh, this an address I would like to use. This is also a broadcast. Understand? And then the IP address would, you just tell the DHCP server. The DHCP server would check somebody using it. If not, it will log you in, then send you the IP address that, oh, you can use it, and then you can also use it. You understand? That's what I think. That's what makes, and this is also more important. It's very important. Right? The JCP server does sends more than IP addresses. It sends the address of the first hop router, sends the name and address of the DNS server, because you need to search for sites. You understand? You need to be able to look up, do a DNS lookup for any site that you want to. You need to be able to tell of the network mask, so that if you're sending a message to somebody who is incidentally in the same network, you are like, you don't have to go far and then go and route somewhere else. You can just do it yourself. Understand? And we can skip a lot of things because none of them are necessary, and then move straight to IPv6 and the N8. Okay. So NAT and basics and generalized forwarding. So that's important. Right? Yes. So you see, when we're talking about the 4.96, I said that it will get finished, right? Because right now, if you check how many phones Samsung just sold, I think last time I checked there were about 350 million or so. So like it's, and those are just phones, right? You don't talk about laptops, you don't talk about, right now everything is becoming smart. Fridges, speakers, toilets, so everything is connecting to the internet. And as the last time I saw a digital ring that you can buy from, I think, Aura or something, and then it connects to the internet and tells you statistics. I mean, so right now it will get finished. Honestly, it will get finished. They noticed in 2011 that it will get finished, and then what they did to, they brought up two mitigation strategies. One was called NAT, right? Network Address Translation, and then the second one was IPv6, right? IP version 6. Great. Yes. Um. Hmm. Yeah. So let's talk about the NAT, right? So the beauty about the NAT, the network address translation, is that if there are several computers connected to a certain network, right, they all use a version of this. I think there are three that they can use. They can use 10.0.0 slash 8. They can use 172.16 slash 12. They can also use 192.168 slash 16. I'm sure if you've ever done local hosts before, you'll see one of these, right? Depending on how your network is built, use one of these, meaning that these ones are your network actually uses this, as it's very widespread now. Your network uses this as your IP address. Now, when you get out of um your network, right, the rest of the internet is just one IP address that it uses. How does this make sense? Because let's say that I'm using a web server that is port 80, right? That means that my IP address is 10.0.0.1 slash 80 or port 80. And unless I'm using the same web server on this port 80, how do you make sure that like I don't confuse the two? What happens is that, let me check if it's mentioned. Oh, yes, okay, cool. What happens is that when you send a message, even if it's the same port, right? What happens is that there's a NAT translation table that will, like, they can really be used, right? What happens is that it can, depending on the number of, like, regardless of the number of interfaces on this side in your subnet, right? It can assign the same IP address but different port numbers. So if you're using port 80, port 80, port 80, it will tell you that it will send one message as 500, it will send another message as 5012, to send another message as 6612. You understand? It doesn't matter what is happening on this side, it will assign the port numbers. And because the port numbers are up to 65,000, it can send as many requests as you want. You understand? And without changing the IP address. So how does it work? So you first send a request, and then when the request gets to the router will change it, right? It will look at what you are doing, look at what is your IP address, and then what is your port number, and then it will look tampering with the message. I don't expect the person to be Like if I send the message to you with a serious voice, I don't expect it to get to you and then it's a song or it's now poetry. You understand? Even though the message is same, I don't expect it to be like that. So it's a problem. Just to deliver my packets with just reliably. That's what I want for a communication device. Don't just be doing things. And that's the end-to-end argument. So we'll discuss why the advantages and then what is actually happening. So that's NAT. NAT is actually very light. I hope you do understand. And let's talk about IPv6. Now, IPv6 was also brought to mitigate against this the finishing of the space of the IPv4. You understand? So the innovations it brought was that it has a 128 bits address. That's very overkill. Like that's extremely overkill. Like we're dealing with this thing, and then you just because if you every extra bit you introduce like um doubles your capacity. And you've moved from 32, you not even moved to like 64. 64 is very overkill. But you've moved on to 128. That's very well. That's sextillion levels of like capacity. You understand? But that's not the only thing it brought. It also brought hierarchical address allocation, brought a plug and play system, simplified packet header. This is very important. See, we saw plenty things. We saw type of service, we saw optional field, we saw version, we saw header length, we saw length of packet, we saw plenty other things, right? But with the IPv4, with the IPv6, it's very, very simple. You understand? It's very, very simple. There are also security features built into IPv6. There's integrity, and then there's enhanced quality of service features for it. So this is the IPv6 format. Is it? It's very simple. Version. This is 6. Priority. So it identifies datagrams among a flow. Now, this is important. This is important. What is a flow? What's a flow? We started by looking at messages as packets, right? Discrete amounts of information that are sent over a wire. But that's not how like it works. You understand? You want it to be sort of continuous, and that's what a flow is. You see, flow is not really well defined like that. You understand? There's no like solid definition for a flow that I can give. There's no solid definition of a flow that I can give, but it's it's sort of like a series of communications, right? Instead of one packet, you have a series of communications between two endpoints. Basically, that's it. You understand? Basically, that's it, right? Instead of it being a discrete packet of information that you're looking at, look at it as a series of it's so one, two, three. This is a flow. This is a flow. Understand? And there's your channel. This is a flow. Great. So this is your flow label. This is your flow label. The payload length. The next header. This sort of like your upper layer header. So is it TCP or UDP? Right. So I think TCP is 17, UDP is 6. Something for you. Hop limits. This is your TTL. Your time to live field. Source address 128.128, and this is your payload. This gives you a constant um length. You understand? So it is actually faster than IPv4 that has to look at plenty things. And very, very simple. Light work. Okay. So there's an IPv6 address, you understand. Colons are usually used to um separate every 16 bits together. And I know what 16 bits are because hexadecimal, you can use hexadecimal notation. It is very, it's easier to work with. Understand? Because it's hexadecimal,